through using Intrepid's filtering tools for line data sets and grids. So I'll just start off by talking about where to find Intrepid's filtering tools, and then talk about the line filtering tool and the two grid filtering tools we've got, which are Grid FFT and the grid convolution tool. Also, throughout the talk, I'll run some demonstration task files and show you where to kind of find it all. And then at the end, we'll field some questions if you guys have any specific things you want answered. So Intrepid supports both spectral and spatial filters, and supports most commonly used ones like your moving average, nonlinearity, high pass, low pass, vertical derivatives, and reduction to poles. In the Intrepid line filtering tool, you'll have a number of different sampling modes. So you can have spatial mode, where each point in the database needs to have an associated X and Y parameter. A time-based mode, where every data point has to have an associated recording time or fiducial. And a fixed sample mode, where there's no associated timings or locations with the data points. You just know that the data point is recorded at fixed intervals. So to start the line filter tool, I'll just jump out of this. In the Intrepid Project Manager, you'll find a number of different tabs up the top here, or drop-down menus. All of the filtering tools within Intrepid are located under filtering. We've got line filter, and then grid FFT, grid convolution, and Wiener kernels, which you can use in the grid convolution tool. I'm not going to talk too much about Wiener kernels because that's more covered by George in equivalent layer methods next week. So if you want to open up line filter by filtering, and then line filter here. It'll open up your line filter window. Just go back to the PowerPoint. Sorry. So for this particular example, if you guys want to follow along as well, you can open the following directory in Intrepid. Go the Intrepid installation directory, then sample data, and guided tours, Intrepid datasets in the Albury directory here. And this will just set the working directory for the line filtering tool. And then if you click on the filtering tab and select line filtering, as I showed you previously, it'll open up line filtering tool. As the line filtering tool is an older tool, it's not Java based, it won't preload a database that you have selected in your working directory. So you'll have to open it yourself in a sec. So in the Intrepid line filter tool, there'll be, again, a number of drop-down menus. To load your data set, you click on File and then Load Line Dataset.
Sorry, Tim, I got lost there. So where's the data again?
So if you go Sample Data.
Sample data, okay,
yep.
Yeah.
Yep. And then, so I'll just bring this up so you can see it again.
Yeah, sorry.
That's okay. No problem. So it'll be here, sample data, guided tours. Okay,
guided tours, yeah. Yep.
Intrepid datasets.
Yep, okay, and then Albury.
Albury.
Yep. Okay, thank you.
It's okay. So just take you quickly through the file menu. You've got a number of options. You can load a line data set. You can save your currently filtered signal as a new field within that database. You can load a custom filter that you've created and also save custom filters. These filters will default to a filter directory within the Intrepid installation directory hierarchy. I'll show you that a little bit later. You can also load options and save options, which will allow you to load and save task files, so you can replicate processing steps later on. So in this case, we're going to load the albury.dir Intrepid database. So if you click on File and Load Dataset, and then as you've already selected the working directory, the Albury working directory, it'll open in that directory, and click on albury.dir. And when you do that, and click Open, you'll be greeted with this box, which asks you what the sampling mode of the data set is. We're going to choose geolocated. You click OK. And then it'll ask you for a signal field. The signal field we're going to use is raw mag. And if you click OK after that, it'll ask for a sensor altitude. Rad alt is the one we're going to use. You can skip this though if you're not wishing to take the altitude into account, just for demonstration's sake. So once you've done that, the line filter tool will display your loaded dataset with the chosen signal in the top window. This signal is unfiltered, and the bottom window will display the filtered signal of the chosen line. You can swap from previous line to next by clicking next and previous. You can also click on Go To, which will bring up a window. I'll just do this now. So I've got our raw mag, our rad alt, and we're not going to choose an optional drape. So this is our signal field and the filtered field. So as I was saying, you can go next to swap between lines. You can also go to a given line within the database. We're just going to stay on the first line. Sorry, I'll bring back my presentation. Okay. Now, if you right-click on the top window, this window will pop up, and this will contain the properties of the line. So you have the line statistics up the top, information about the spacing of the samples of the data points within the line, the interpolation method that you're using to display the line data. This is purely a visual aid for the signal, so it's basically user's choice on what they want to use. You've also got a detrend method that you use to detrend the data up the top, and a line direction indicator in this area. For the display of the lines, you can choose to overlay the filtered line on your raw signal field. You can choose to tick to zoom both lines at the same time, so that when you zoom in on a particular area on one window, it will zoom in on the same area on the other. And you can choose to detrend both the raw and filtered lines at the same time. So if we want to apply a filter to our line data, we can click on the spectral drop-down menu up the top of the filtering tool and choose new FIR Fourier, and then vertical derivative. So this will bring up your vertical derivative filter properties window. And you can choose the name of the filter. So it defaults to the filter's name within Intrepid, but obviously you can change this if you like. The order of differentiation for the vertical derivative, so you can have high orders if you like, and the number of weight control points for your vertical derivative. You can extend your data. Sorry, go.
Excuse me, Tim.
Yeah.
Can you expand a bit on the number of weight control points? Is that something we can change, and what does it do to the data?
Sure. So that is changing the number of points that is used to calculate the vertical derivative at each point, data set point. The more weight control points you use, the larger trend of the vertical derivative it's going to take. You want to basically tailor it for how many data points you have along the line.
So is 12 like the default, and you can change that?
This is the default value.
Yeah.
Yeah, and you can change it if you like.
Okay. Thanks.
There are also a number of different roll-off options that you can choose, and the roll-off window size as well.
Returning to the weight control points.
Yeah.
There, I'm not sure that I kind of understand, since we're doing okay, this vertical derivative, it's a moving window filter.
Correct.
Not right. Okay, not a Fourier. But it says, because if it's a Fourier filter,
yeah,
I would have thought there's no real weight control points. You Fourier transform the data for a line and then alter the Fourier coefficients and then transform back again.
Yeah.
So I'm not quite sure where weight control points come into it.
I'll get some clarification for you on that, Richard,
yep.
And I'll send it an email after this session.
No worries, thanks.
No problem. So once you've applied your filter, it will display in the bottom window, and the filter is only applied to the current line. If you want to apply it to the rest of your data set, you need to click the process button down the bottom here. When you click process, you can choose individual lines or a range of lines, or all the lines in your data set. And once you click OK in that process window, the filter will be applied to the selected lines. The database in Project Manager won't actually update until you've closed the line filter tool. So after you've applied the filter and processed it, don't go try using that data set until you've closed the line filter tool. If you want to, you do have the ability to define your own filters. These can be accessed from the file menu, as I demonstrated in the line filtering tool. And when you select it, it will automatically populate the current filter with your filter settings. These are saved as a .fdf filter description file. And by default, they're saved in the Intrepid installation directory, the extras, and then filters. So the installation directory, extras, filters here. And there are a number of default filters available within this directory already. just lastly, on the line filtering tool, you can view the power spectra of your data, and you can save the components of the power spectrum to a CSV from this window. I was just going to very quickly go through. There's also the ability to handle tensor data sets. So I'll just quickly go through the. I'll show you that. So we've got our data in sample data, QuickBooks. Arizona. So filtering line filter. Load our line data set, it's geolocated. And this is our tensor field. We're not going to select an optional feed for the moment. Skip these. You can see the tensor data set is opened within the line filter tool, and you can apply filters to this tensor data set that will apply to all the components within the tensor. There are examples that'll probably down in, sorry, I'll just bring it up. So I think I didn't explain before as well. Adam, you'd know this, but within Intrepid, we ship a large number of worked examples and especially example task files. We try to have a task file for each point of functionality within Intrepid. You can find these under the sample data examples directory. Let's close this. So installation directory, sample data examples. And down here in tasks, task files are split up based on the drop-down menus above from the project manager. So if I go examples, tasks, filtering, and line filter.
Can I ask a really quick question, Tim?
Yeah, of course.
So this is unrelated, but yesterday I was playing with I was having a look at the data sets.
Sorry, you're a bit quiet there. I can't really.
Oh, sorry. Is that better?
That's perfect. Thank you. Sorry.
Yeah. So yesterday I was having a look, and what I was interested in was having a look at the magnetic tensor gradients.
Yep.
And there's a little README file there saying that there's two data sets. One is like Canadian mag tensor, and the other one is from Germany.
Yep.
And the German data is there, but
But
the
Canadian squid tensor isn't?
Yes.
Yes. That was originally in the data, sorry, the installation provided to GA, but we've since had been asked to remove it from our training data, our example data sets. So we've removed it, but the documentation hasn't been updated to reflect that.
Okay.
I might, if it's something that you're interested in, I can have a chat with some of the developers and see if we can find another tensor data set for you.
Yeah, that'd be really good, because the German one, the Fluxgate data is buggered. So I really wanted to compare the mag tensors with the Fluxgate and do a bit of analysis. Yeah.
Okay, no problem. I'll pass that on to the developers, Adam, and we'll see if we can get you a different data set. Yeah. Okay. Also, I had a bit of a question the other day about detrending, and I just wanted to expand on that, especially in the context of filtering within Intrepid. Detrending is always used during spectral processing methods within Intrepid. When you're trying filtering or a data set that has long wavelengths, especially wavelengths that are much larger than the range of the data set, they won't be correctly represented in the frequency domain. This is because there are a few assumptions made when utilizing fast Fourier transforms. The fast Fourier transform algorithms that Intrepid uses are based on discrete Fourier transforms. And these are only relevant where discrete values are observed within the data. And the data must also be periodic. So you can facilitate this by resampling the data onto an even spacing, but you need to introduce dummy data, and introducing periodicity into the data creates a step in it. You need to be able to deal with this step, and so we do this by detrending the data as part of the Fourier filtering. That goes on behind the scenes, but you can also use this detrending when you have IGRF that you want to remove, or you're only interrogating a small area of interest where the larger regional trends are not of interest to you. You can also, having a very large trend in your data that causes a large change in magnitude can make it difficult to interrogate small variations in your signal. So you may want to remove this large trend. And so this is just repeating what I was saying before. The example task files for line filtering, grid filtering, and grid convolution tools are located in the examples, tasks, and then filtering directory in the Intrepid installation. Similarly to the line filtering tool, Intrepid offers filtering in the spatial and spectral domains for grids. It's grid FFT, spectral domain, and a grid convolution for spatial. The grid convolution uses formulas called kernels to adjust the grid cells. There are kernels that ship with Intrepid, but you have the ability to create your own within it as well. Again, the grid FFT tool offers a large range of enhancement products. You've got low pass, high pass, RTP, directional cosine, match filters, all kinds of stuff in there. And it operates in the Fourier domain, which allows fast processing of the grids. And there's also full tensor Falcon support as well. So you've got the grid data set as your input, process specifying your filters, and you can examine the power spectrum, and then the output will be your new grid data set after the data has been brought out of the spectral domain.
Just going back,
yeah, of course.
Managed to break in at the time. You were going through the line Fourier transformation,
yeah,
and you were saying that a resample happens to get to a convenient number, power of 2 or something or other. You don't do that by padding, you do that by resampling the actual points. Is that what?
It's a mixture. Yeah, a mixture of both.
Right. Yeah, not sure that resampling the points is such a great strategy for doing that. how can we do anything to control that?
Look, not to my knowledge, but again, I can mark that as something to get back to you about, Richard, if you'd like.
Yeah, that'd be good.
No problem. Sorry, I'll just write these down so I don't forget.
No, that's wonderful.
Yeah. Okay. So using the grid filtering tool, it's opened from the filtering menu in the project manager, and it's the grid FFT option. When you open it, it will prompt you for a grid to load. And the grid displays in the spatial view in the grid filter window. Just running through briefly, there are a number of available FFT filters in this window here, and you can add filters to the filtering process stack by clicking on one and then clicking this little arrow here, and we'll move it across in between grid conditioning and grid restoration. Clicking on each of these filtering process steps will change this context sensitive menu. So you can change different parameters for each step. There are two views down the bottom here. You've got your before and after in the spatial view. You can change your lookup table of the grid to be histogram or linear by right-clicking, and it'll just come up with a little menu to choose between the two. Once you've set up all your filtering process parameters, you click apply, and it will run through the grid filter and give you a preview of the after image. This after image window is great for very quick verification, but to interrogate your data, your grid, output grid more closely, it's best to use the 3D Explorer because you have way more options with visualizing the grid. Now, I was just going to run through a very quick grid filter example. It's very similar to the one I actually ran on Monday, but I got some clarification on one of the steps that needed to be performed. So I'll run through that now very quickly. So we've got our data set in sample data, cookbooks, magnetics, reduction to pole. The grid we're going to use is the Sangi Mag Raw. So I'll open that up in Grid FFT. As I said, clicking on the tool prompts you for an input grid. We've already got ours selected because we had it selected in the project manager, so we'll click open. This brings up the grid filter window. As you can see, there's different filters available here. You can also choose the way you want to display your input spectral parameters in terms of either wavelength or frequency, and you can change the multiplier over here. So it'll just tell you number of cycles per meter or your cell size. So we're going to choose a reduction filter, move that across, and that brings it into the processing stack under grid conditioning. So we've got our input grid. You can save the FFT of the input grid as an output, and you can choose where you want to save it as well. So we might click that, and that's going to default to a temp directory. Let's say we want it in our working directory. sorry, wrong one. I'll put it in grids. Save that. You can also set some pre-FFT grid conditioning. You can expand the grid FFT border. So I've got a Yvette's saying she doesn't have magnetics under cookbooks. Does anyone have it? It should be in the installation you were given. Yvette, maybe I can troubleshoot that afterwards.
Okay, no problem. I can follow what you're doing. That's fine.
Yeah, no problem. Sorry about that.
Thanks.
So you can choose how large you want your FFT padding to be. 120 would mean 20% padding on each side. You can remove trend and choose the degree of the trend removal, and also introduce grid edge roll-off to reduce ringing artifacts from having harsh boundaries on the edges of your grid. You can also save various intermediate grids that are created throughout the process and reports as well. With the reduction properties, you can, for this particular reduction to pole, we can use this tool to account for the IGRF. With this though, I'm just going to, for the purposes of this, leave this as default for the moment. This particular data set is a low inclination, so we can choose a low inclination and it'll set the inclination limit of 20 degrees. And it's a special algorithm to handle data that is close to the equator. You can also add your directional cosine roll-off in this step as well. You can choose to reapply a trend on output that was taken out. That'll depend on the filters that you've chosen to use. And then finally, we've got the output grid data set, which is just defaulting to our working directory. So I can click apply. And that'll give us a reduction to pole grid. You can also view the input spectrum filter response and filtered spectrums and the radial power spectrums as well of the filtered and non-filtered filtered grids.
Can you just explain the low inclination and what that does? Like, so we know if we can have any confidence in doing that in low inclination mag data sets?
Look, I'm not an expert in it. There's significant documentation about it within the Intrepid online documentation. It will take you through the assumptions made for the low inclination option. Might be best to have a look at, have a read through that. And then if you've got any questions beyond, you can send us a message and we'll go into it in a bit more detail, if that's okay.
Yep.
Yep, no problem. So, and this is just a little bit about the different types of filters available. There's bandpass, which you specify your upper and lower bounds and define the extent of the filter. And that'll give some more options for cosine roll-offs as well within the filter. There's vertical derivative filter, where you can choose a degree of vertical derivative, so like first or second degree. And this particular filter can cause numerical instability larger orders of derivatives, and enhanced noise as well. So it can be a good QA/QC tool to check the quality of your original data. Downward continuation as well, where you are estimating the signal below your observed signal. It's basically a high-pass filter that has exponential growth, and sorry, I've had a blank. Oh, sorry. The units are you choose the level that you want to downward continue to. Sorry, and the number that you use is in units of the spatial data that you've chosen for the grid. So it'll be in meters for most of the time, or degrees if your grid is defined for latitude and longitude. Because of this exponential growth in the high-pass filter, it causes numerical instability. And you can see the signal breaks up the further down you go as well. And then there's a reduction of the pole, which we've talked about briefly. The last filtering tool that Intrepid has is the grid convolution tool. And it's a spatial convolution method. It uses kernels, as I was saying before, to perform the convolutions. And these can either be user-defined or there are a number of preset kernels within the tool itself. The kernel files specify the weighting for the center cell and the neighbors around it. So you can think of the kernel as basically a matrix with weights in each of the matrix elements. So for this noise estimator, for example, you have the center cell of 1 leaving the currently interrogated cell as its original value, and reducing each of the cells around it immediately up and down and left and right by a multiple of -0.250. The convolution filters can get quite large, and there's no real limit to the size you can make it, but like it'll just depend on your use case. With there are tools like the Wiener kernel tool that will allow you that will help you create your own kernels to use with your own processing, and specifically for the data sets that you're working on. So the grid convolution tool again is open from the filtering tab, and we'll preload the file you have selected in Project Manager, like the grid filtering tool. There are 3 kernel options. In the window, you can load a kernel file. You can use a preset kernel that is intrinsic to the tool itself, so it's not a separate kernel file. It's actually incorporated into the tool, and you can construct there's a kernel constructor tool as well. Just running through some of the preset kernels. There's a median value kernel, and it'll adjust the value of the target cell based on the median value of the cell and its neighbors in the window. This will have the effect of smoothing out your grid. And the only input for this is your window size. So as you go up in window size, you get a smoother and smoother grid. There's a contrast normalization filter. It enhances the low amplitude, high frequency content within your grid and dampens the high amplitude content. It's similar in effect to an automatic gain control filter. There's a Gaussian anti-alias filter. It's useful when you have high frequency data that's along your survey profile lines and can remedy your aliasing that is occurring with wavelengths that are less than the line spacing of your data set. The final preset kernel that's offered within the tool is the terracing filter, and it classifies zones in your grid derived from ideally underlying geology. So it basically works by finding minimum and maximums and working from these points to fill hills and valleys to get even areas, almost like terraces, to reveal ideally bounding polygons. Originally, it was asked for by USGS for radiometrics data specifically. So I'll just very quickly go through. We've got tasks area, a grid convolution. So with these examples, if you can click on them obviously and see there's a short description about what they do, and then there's the commands to write it out. But what you can do is preload these into the tool by right-clicking and clicking Open with Task. This will bring up the grid convolution tool with the settings specified in the task file preloaded. So we've got our Newcastle radiometrics, terrace, kernel, number of iterations, maximum percentage flattening, and our output grid location. So if I run that, get a message saying it's completed successfully. And that has attempted to find bounding polygons within the grid. There are a number of different task files throughout that will cover the different preset kernels. No task files though that will, so I'll just bring it up, grid convolution. I'll see if, because I had this task file selected and opened the convolution tool, preloaded in, but, oh, sorry. There are no current task files for using these user settable kernels. You can experiment and try them out for yourself at a later date. But I mean, I know it's been kind of lightweight. Did you guys have anything in particular you wanted to go through in a little bit more detail?
Oh, could I just ask a question on what you were showing just then?
Yeah.
So you've got the preset kernels, and then there's kernel type, and there's quite a few different options there. So there's curvature, median, Z-norm, Gaussian, terrace. You just showed us what terrace would be good for the radiometrics. What would the other ones, what would be good uses for the other ones? So I assume curvature must be, gravity gradiometer tensors.
Yeah.
What would the other one, like where would you use each example?
Look, I'm not exactly sure, but I can, again, come back to you a little bit later with some potential use cases for each, if you like. I'll send you an email a bit later, if
Okay.
you like.
All right.
Yeah, I think that would be good if you can give us, some examples where it's best to use some of the kernel types. That will be helpful.
Yeah, no problem. I'll put together an email with the what each of these kernels would be best the best use case for. That's no problem at all. Was there anything else you'd like to ask or see, or? If not, that's okay. I think Diffu, who was giving a presentation yesterday, wanted to, apparently something didn't work quite the way he expected, but he's worked out what went wrong, and he'll wants to just very quickly go through that again with you. So maybe we'll take a 5-minute break, and when you come back, Diffu will be here to just briefly go through that with you again, if that's okay.
Yeah. Okay. Thanks. Can we start at 12 then? It's 11:53 now or something.
Yep. Sorry, 12:10.
12:10. Yeah. Is that okay?
Yep.
Is that okay with everyone?
Yeah, that's good.
Okay. Good.
Yep, sounds good to me.
Thank you. Thanks very much, team.
No problem.
Thanks.
Thanks, guys. And
Thanks,
yeah, with some of those questions, I'll get a better response to you as soon as I can.
Yeah, and sometimes we may come across things that we would like to, questions that we would like to ask, which we probably may not have asked today. Is it okay if we can send those to you?
Yeah, absolutely. Look, send it to, I think either the support email would be best.
Okay, yeah.
Support at Intrepid-Geophysics. Because that way everyone will be informed of the request, and
okay.
it'll be able to go to the person who's best able to answer it. But with those specific ones you brought up, I'll follow those up for you guys.
Okay. Thanks, Tim.
No problem. So yeah, we'll take a break and come back at 12:10.
Hello, Richard. It's me.
Hi, Diffu. How are you?
Yeah, not too bad. And yourself?
Yeah, getting along.
Yeah, it's a long time. It's a long time.
Yeah, it has been a long time, eh?
It's a long journey.
Yeah,
So how's everything going?
yeah, enjoying the work.
Yeah, it's great.
Doing a lot of gravity at the moment.
Yeah.
It's a bit different. It'd be all this stuff this year is making life pretty difficult, eh?
This world is crazy.
Yeah, unbelievable. But no, we seem to be doing okay. So fingers crossed.
Yeah, great. I'm really glad to see you here. Yeah. Oh, sorry, I just grabbed this. Since everyone is here, I just want to grab 5 minutes, to correct my mistake. I made it yesterday. That's all right. I want to show you something new in regards to the Python bindings stuff. The first thing is this GitHub site for Intrepid3D Filtering. If you have an account, you can just log in. If you don't, it doesn't matter. This page is public, so we publish some projects in public domains. One of them is this Intrepid PY, which is the batch library. So you can see source code and the test. Well, currently in the test, there are a couple of examples. The reason why I want to show that is yesterday I was asked whether the Python script supporting this repeat blocks and that kind of things. So I made a quick example. So on the test. So there's one I can probably show you later how to run it. And so this is the example. So if just for free, to pop yourself in this project, and this will be a very how can I say, a hot area in the near future. And so I guarantee you there will be a lot of activities on this. So let me just simply try to compare. So this is the script that I made last night, just to show you how to write some Python script to handle the repeats. It's very simple, other than writing the repeats in a text file on the right side like this import block. You just simply define this imports into an array and then run a for loop. So this is a very traditional coding thing, nothing special. So to run it, it's very simple. Let me just simply jump. So this is Intrepid. Let's just simply jump into this lovely import where I have only this one py file sitting here. So you get file and create a new command window. So Jeff Manager will open the command window in this working directory. So simply call this Python script Python 1. And from Jeff Manager, you can see, it's executing the script, doing imports and that kind of things. And this script just simply demonstrates, how do you run repeats from a Python script. And so this clip line thing is the one that yesterday I didn't manage to run due to the environment problems. So let me just simply finish this off. So see this clip line. Yeah, have a quick look. So there's only one py file. It's simple, just py -n and clip. Yeah. So this one just simply copies the data sets from the Intrepid installation directory and then do the action you ask it to do. Yeah, that's simple as it. I think. Is there any questions?
This may be really obvious, but you're using Python to do various tasks here.
Yes.
The difference between doing things via Python and doing things via a task file.
Yeah. So what the difference is between that is this repeats block on the screen. You can see this repeats block on the right side, and this is quite ambiguous. in the task definition, because as I said yesterday, the task file is not a programming language. And if you have more than one field, it becomes a little bit, unclear whether, these fields, they're, orthogonal related to each other. So how do you expand these task files? As a programmer, I really dislike this. So in Python, this is a straightforward way. You define an array, and then you can do whatever you want with that. And the other thing with task file is a text format, and you can see what is slightly different from traditional JSON. And I said JSON will be supported very soon. There's no problem with that. But this task file is a text. With the Python script, you don't have to authorize a text file. You just simply write your code in a natural way. So these will probably be a little bit more familiar for developers. And also the text file is not that stable. I mean, in the near future, there could be quite a bit of significant changes to the format of the task file itself, especially these repeat blocks. This is something I really try to get rid of, because there's some glue code in Intrepid try to handle this in a very how can I say, in a cloth way. So I want to remove that. Yeah, but right. In the near future, I think the Python has shown its power, and I'm going to focus on this and put more resources into. And I encourage everyone to use Python because you can debug these kind of things. It's a lot right. easier than the text format. Yeah.
Right. The Python that you're using here, is it something that is part of the Intrepid install, or does it rely on having Python already installed?
No, the Python thing is just a standard Python. Yesterday I installed Python 3.7 on this computer. And all you have to do in order to use the Intrepid library is you have to install, I'll just simply show you the command. You just simply install this Intrepid protobuf.py package. So this is a Python package. It's via pip. So you just simply run this command once, and then this will make the Intrepid Python bindings and the library itself available across the whole system. And after that, you can do this, on any command line environment or that kind of thing. It'll be available, to all the users across on the system.
It's probably James. Is James still there?
Yep, I'm here.
Oh, where do we get our Python version from?
So we have it installed with one of these IDEs usually, or with something like Anaconda, the Conda packages and that sort of thing. And so we do have the latest version of Python and that sort of thing for Windows 10. The only issue that we would have at GA with our Windows 10 machines is we're not always able to install these using the pip package ourselves. Even in the Windows 10 dev folder, there's some issues. So I've found you might have to use your own personal laptop to do this install.
Yeah,
that was going to be my next question, of whether we were going to be allowed to do this.
Yeah. Thank you, Richard and James. So this will be my question, to GA, because yesterday I thought of this question, whether in GA you are allowed to install packages by pip. If this is a negative answer, and I'll probably need to find another way to do that. Say, for example, allows you to, you can just simply download this package and then run this build, this Python setup py as dist, and then install it on your local computer. Well, if you can use pip. I think it doesn't require any administrative privilege and that kind of things.
James,
that part seems very straightforward.
Yeah. So I thought this build kind of thing is for developers. before I thought it probably, for GA, you don't have to run this, and this is left for me, to run this, to test it on my computer. But in GA, if you find difficulties installing this library by pip, you can just simply grab the source code and do it by yourself.
Yeah, I can give it a go and see if it works on our machines. But yeah, in my experience so far, I haven't been successful. It's just an issue with how our security is set up on our laptops.
Oh, sorry about that. Sorry.
But we should be able to use it on our own personal laptops with no worries. It seems pretty straightforward.
You give it a go. If you have trouble with that, and let me know. But I'll try to correct this, and together we can probably find a way around this.
Yeah, thanks, Diffu. I appreciate it.
No worries. Yeah, thank you very much. Yeah, thank you, Rita, for your time. Thank you, Richard. I'll probably leave the room. And take care.
Good to see you.
Thank you.
Good to see you.
Thank you.
Good to see you, Richard. Yeah, bye-bye. Thank you.
James and Richard, like I was talking to James the other day and said how it's good to have people who can multi-program, whatever, multi-software users.
If you could sort this out, James, I can see like Python's turning up everywhere. If we can't do much with Python, then it's going to be a bit of a restriction.
Yeah, I totally agree. Yeah, I guess the one of the benefits of how Intrepid is installed is that you can just take the USB dongle and plug it into your personal computer. But obviously that's the best way is to have it working on Windows 10. Yeah, I might put in an IT request and try and get it up and running. Yeah, because I totally agree with what Diffu's saying about the repeat loops, because we used to do a few of those with the job files in the past, and they are a nightmare to use. They're just not that intuitive, and they're very hard to write into the files. But with like a for loop in Python, it would just be really simple.
I would have thought you would have just cut and pasted multiples in the job file.
Yeah, we did that a lot actually.
No, it looked interesting that. It's turning up all over the place.
Yeah, it is. It's definitely become one of the most popular programming languages, and it is. It's in everything now.
Yeah, we've just got to get some.
Do I go with learning MATLAB or improving my MATLAB capabilities, or Python?
I think they're quite complementary. They're completely different, I think, in scope.
I would like to add, that was a good point. I believe Python has an interface into some MATLAB capabilities. There is a bit of a connection.
Sorry, Tim, you're a bit low there. Can't hear you properly.
I believe there might be some Python libraries that allow an interface between Python and MATLAB. So if there are things that you know how to do in MATLAB, my understanding is that someone else has probably done it in Python. So that's also something to consider. But I just need a few more seconds to get my documents and my slides ready, and I'll be ready to present grid modes today, as well as address some questions from yesterday's gridding topics.
Yeah, using arrays is certainly a strength of MATLAB, as are the graphics. That's my impression. If you're doing anything, if you're anywhere near the web, Python's obviously the go.
I haven't used MATLAB anywhere near enough to tell you which one is better for the work we do, but I know Python does have lots and lots of packages, and one of them is called matplotlib, which is designed to, as far as I know, essentially be a ripoff of MATLAB, and give you all those graphing statistics sort of things as a package. And there's lots and lots of free stuff available online, and lots of community user support and all that sort of stuff, which makes Python a very attractive package to use. But I don't know enough about MATLAB to tell you which one's actually better.
Yeah, I think MATLAB's a much higher level. things. You get commands, very powerful commands, straight off for doing things with matrices. So any linear algebra, any matrix operation is very easy in MATLAB, which means grids are very easy to deal with. Image processing of grids, that's, to me, is the strength along with the graphics. You don't have to be quite as neat and tidy as you have to be with Python.
All right, excellent. I'm ready to start if everyone else is all good to start with the demonstration for grid merge and gridding operations today.
Sounds good.
Cool. So just to start off, there were some questions yesterday regarding some line data and how variable density could be an alternative. I had a shot at merging some line data at 60 meter, or sorry, 300 meter recordings and 500 meter recordings. And what came through was a slight artifact where the lines become too close. And this is a result because the minimum curvature tries to honor both points, and it simply can't create a nice polynomial between the two of them, and you get this really ragged looking thing. Alternatively, here on the right, we have a product produced using grid merge when you have 60 meter cells and 100 meter cells, where this region here that I'm circling with my map cursor is about 60 meter, and the region outside that is 100 meters. So that's an application for the meantime for grid merge, and it's where, or why it might be important to use it. There were some other questions about relaxation factor in gridding. So this is, the relaxation factor is just a value, a constant to speed up the interpolation process so things don't just hang or become incrementally too slow. It just modifies the value each iteration by a certain amount. By default, it's 1.375, but you're free to change that. There was a question regarding tension. So the tension in Intrepid, where if you specify 0, you are using minimum curvature, and the closer you get to a value of 1, you start using a different condition where you're no longer adhering to Laplacian fields and constant curvature and things like that. And instead you start getting sharper faces, which is applicable for gridding topography or other, the application I think of is topography there. And the last question, I think, was about where the origins and the centroids are defined. The uppermost left, so the northwestern point of the grid is the origin, and it's calculated to be this nearest multiple that will capture the extents, or the first multiple that will capture all the extents of the input data. You can control that using the top left, top right, bottom left, and bottom right coordinates in the gridding menu. And you can shift that by half a cell or whatever you see fit for your data. But it definitely doesn't automatically align over a line set. It actually just captures the region that you wish to grid. But those questions out of the way. I believe there was another question for kernels earlier that was addressed to Tim. But yeah, this is a grid merge. So grid merge was first released in 2000. In historical products, it was called grid stitch. And it's designed for merging gridded databases of varying dimensions and sizes together so that you get cohesive and clear pieces of work that you can interpret and look at. Being tied in with Intrepid, it means that we can use the task file syntax and the concept of repeatability to reprocess our data from the very base level as line data through to gridding and then grid merging again. And we can repeat that process as we see fit. And whenever we have a new survey done, or alternatively, if we only have the grids, whenever we get a new survey, we can bring those into the pre-existing grid. So they're two strengths. The limitation of bringing a new grid into a pre-existing merged grid is that you should only do it a number of times. Each time you go over it, you're generating a least squares fit on top of a previous least squares fit. So we have a bit of a recursive generation of uncertainty. So it's recommended to not do that and to always start from the beginning or the earliest point as possible. The grid merge tool consists of a standard workflow, which is a DC shift, which is a reference to electrical engineering and a direct current shift, a surface adjustment or a tilt adjustment, depending, which is a trend removal. And then you have your feather merge. There is a pasting merge, but the feather merge is the typical way to do it. And that gets you that nice seamless edge on your grids. So yeah, that's what I'm saying. The standard workflow will take your individual grids, bring them all to a common reference, so we can look at data that has been diagonally corrected and ones that haven't, or ones that have had the IGRF removed, or could be gravity data that's been leveled. It's going to bring it to a common shift or common scale, and then begin the workflow. So as I was saying, this is the DC shift. For magnetics, we use DC, and for radiometrics, we perhaps use a scale and shift instead. And it's often the first step in the process, and it's the recommended step, because it's going to be difficult to bring together two grids that one's at 5,000 nanotests and another at 49,000. It's obviously not coherent and cohesive at that overlap. This is the next track for the surface adjustment. If you're curious to see how the back of it works in terms of how the polynomials are fitted across all the grids, but it's a difference, it calculates the difference between two grids and iteratively removes this difference and minimizes it so that a long wavelength is adhered to across the overlaps and across all the grids. And then the alternative to a surface adjust, if you have the data available for magnetics and radiometrics, is the tilt adjust. And it's going to utilize a database that contains your long wavelength data, such as your AWACS data that you guys would be familiar with in Geoscience Australia. Obviously, this is a beneficial idea to use, beneficial to use over a surface adjust, because you are calculating a least squares fit on real data, rather than an iterative process where you're calculating a least squares fit upon a previous least squares fit, which is what the surface adjust is doing. So you just do have a closer relationship with your data, a bit more certainty, which is a good fundamental to have. The final step, which is probably the main part of this process, the one that's the catchy, how to get seamless edges, is the feather merge. The merge process will use a ranking system. So by default, the highest ranking will be your smallest cell size. And then if a data set has more points than an equal cell size grid, it'll be ranked higher as well. If you choose not to specify, it'll use the system as the criteria. Otherwise, you can manually specify what your quality or your ranks are for your grid. So if you have an idea of what grid's good and what one's not, this is where you can put your foot down and force the process to go the way you want. This step consists of a filter length, which you can specify yourself. It has a number of iterations that run through it, and I'll probably explain that a bit later when I do the demonstration. There is this idea that grids need to have a sufficient number of overlaps, and I cover that here in this point here. There's a minimum number of points in an overlap between two grids that must adhere to. By default, this is 500 points, but you can control this how you see fit. If it doesn't meet this criteria, the system will fail, and it will say that you don't have enough points to calculate a statistical answer. Yeah, so the demonstration today, we'll be looking at our grid merge directory. So it's an Arnhem demonstration. So this is magnetic data up in Northern Territory, in the Western Arnhem Land, I think it's called. So I've got here a Google KML file just demonstrating where the area is, so we have a bit more feel of what the data is. But the first step you can do from your own computers, or I'll run through it, is using and viewing the outlines using two tasks. So I'll begin that now. Here under our sample data, guided tours, and our grid merge, we have our task files, and we also have our raw data and some stitched example grids. So the first task file here, grid merge underscore outline 1, will create the outlines that we wish to look at, and grid merge outline 2 will view them in 3D Explorer. But for the purpose of demonstration, I'm actually going to do this first task in the GUI itself. So I'll head into the raw directory, and I'll choose to go gridding and then grid merge. The first process I want to do is to look at the outlines. So the choice I'll make is to look at the process grids and then prepare a boundary view of the grids. Now, Intrepid grid merge will choose directories. And once you specify that directory, it'll use all grids possible within that directory to do its work. So you do have to set up an input directory at the very start, and each step goes to a new directory and becomes the input to the next step. So here, I'm going to specify this as the input directory by selecting any file and just pressing open. It's going to prompt me if I want to add more directories to the system. In this case, I'm not using more directories, so I'll press no, but in the same way, you press yes and you specify another in the same fashion. It's going to provide me some information, but we can just ignore that. And now we get to specify our outline image directory. So for the purpose of this, I have to make sure I put specify my directory to be grid merge _ outline, just so it works for task file later. But there's no rule as to what it should be. So I press enter and it saves. And I'll choose to use a reference grid or use a reference, and I'll specify the cell size to be 100 meters, just so the process is a little quicker. And it'll ask me if I want to proceed. And it's a very quick process, and it's completed. So I can close this report file, but if you wish to have a look when you do your own processing, this will contain some information, statistics about what's just happened, some extents, and some origins. For now, I'll head back to the upper directory level, and I'll use the outline outline 2 task to take a look in 3D Explorer what our outlines are for this process. And this can take a little bit of time as it's generating a few grids. And because 3D Explorer likes to have a black background, we're just going to quickly change it so that we can see it a bit easier. But here we go. We have the outlines for our grids. We can see which regions are which. We can progressively go through them and figure out the names of each one. But eventually we can see that by using the system, we can define what our high ranking grids are. These grids here, I know are a small cell size, especially over these 2 larger background grids. So these ones here, I want to be higher than these 2. And that's something that I'll keep in mind when we start specifying our rankings. In particular, our Beatrice mag is our highest ranking grid. It's our finest one that we have. So that's in the region just here, in the upper area 1.
What format are these outlines?
These outlines are in ERS. These are grid files. The alternative is that you can use the gridding operations tool, which I'll demonstrate later today, to generate shape files or .ders, which will have the outline just as a line instead of a grid. Yeah, it's just a matter of preference if you want to generate ERS or DERS. It depends on which way you want to go. There are task files in this directory here that demonstrate how to do both. So there's one here, create grid outlines, which will be using the grid operation tool, gridop. Alternatively, this one here uses the grid merge tool. And they produce similar comparisons. So I'm just going to close 3D Explorer so I don't have it in the way. And we can head back to our grid merge window and we can begin our process. So I choose to start my process off with a DC shift. So I'll select this and I'll specify my input directory as the raw directory. And I'll open it and select another file in there and press open. Again, I choose not to have another directory because I don't need it. There's one person waiting to join the call. Is that someone I should be inviting in? Is anyone aware? They're unnamed.
Not sure. We can't see.
All right, I'll wait to see if I get a notification.
Okay.
I'll wait unless someone
Could
tells
be
me otherwise.
Matthew.
Maybe it's Matthew trying to come in. I don't know.
Shall I admit them?
Yeah.
If it's Matthew, yes.
Yeah,
It
we'll quickly tell you whether we'll throw them out.
Yeah, sure. Hello to the
That looks
person
like
that's
one
just
of us.
joined. Is that Matthew?
You're unmuted. Hello. User 44511.
Hello, that's me, Matthew.
Thought so.
That's Matthew. Okay,
Yeah.
Matthew, can you right click on the participant list and change that U544 number to yourself?
Excellent. Thank you very much.
Please.
I'm all good to continue then?
Unfortunately, we'll
Yeah,
have to
sure.
keep him. Yeah.
Right. All good.
Well done. Thanks,
I'm not
Matthew.
going to specify another directory. So I'll press no and I'll press OK to skip this dialog here. And it's going to ask me to specify an output image directory. In this case, we are doing a DC shift. So for the manner of the demo, I'm going to call it demo _ DC. And I'll press enter. At this stage here, we begin to specify our rankings. The rankings aren't used in these earlier processes, but it can be specified as early as now, just for the sake of simplicity. So the base grid that this demonstration uses is the West Arnhem. So this is a 100-meter cell size grid, and it contains the Earth magnetic field still. So it's still about 49,000 nanoteslas. And the idea being here, all the other values are going to be brought down to be level or equal with it, or brought up to in some cases, so that we're all looking at a similar scale, similar magnitude. So I select West Arnhem, and I slide it across to my selected grids, and I press OK, because this is the only base grid I wish to use. My next step is to specify my high ranking list. I could go as far as I want into this, but for this data set, all I need, or this demonstration, is just the Beatrice mag. It's the highest one. It overlaps 2 other grids, so I need to specify it as the topmost one, otherwise it might get put below. So I press the drag across, put this Beatrice mag in the high rank list, and again I press OK. And in the same fashion, I specify my low ranking grid. And in this case, the low ranking is the Millingimby sub. So it's the easternmost segment, or the large eastern segment of the outline I showed before. And it's the lowest cell size compared to the other large grid. I believe it's the oldest, but I'm not sure of the history of the data for certain. But I put it across and I press OK. In this point here, I can specify an overlap limit for this demonstration, and most of our defaults are set on our practice. So a 500 default is just fine for this this work through. So I press OK, and it asks me if I want to proceed, and yes again.
What do you do if you only have 2 grids you want to merge? Do you have the base grid as the low ranking grid as well? Do you select that?
The base grid doesn't have to be either the high ranking or the low ranking. It's just the level that you wish to bring everything to. So your base grid could be your low ranking, or it could be your high ranking. If you choose not to specify, if you only specify one as the high ranking, inherently the next one becomes low ranking anyway.
But you still need to make a choice. You still need to put something into that low ranking.
You don't need to put anything into the low. You don't need to put anything into the low ranking grid, but you do need to put something into the base grid.
Yep.
So there are only 2 ranks, high or low. The base grid is just the level which you want your data to appear at. So that isn't a required step, but the high ranking and low ranking has a default system that'll calculate stuff.
And what if you've got like 3 grids overlapping each other? How do you rank?
Right.
Them
in that case, this is what I was demonstrating. If I can pull up the outline again, sorry, one moment. This Beatrice mag that I ranked as my highest is on top of 2 other grids. So there's no way to specify how a high ranking sits over another high ranking. But in this case here, I have the Beatrice mag, which is a small area. I have area 1, and then I also have the Millingimby here in this region here. So we have 3 grids that are all overlapping. I want the Beatrice mag to be on top, so I specify it as my high ranking. And I also want area 1 to be above Millingimby, but not above Beatrice. So I leave it with no ranking, and I force Millingimby to be the lowest rank. In that way, it kind of sandwiches around area 1, and Beatrice is definitely on top. So it takes a bit of working out, and depends on your data.
So is that high ranking because that grid has like lower cell size or something? Or is that
so
like if you have infill? Yeah.
Yeah, so this Beatrice mag has the finest cell size has a small cell size in this set of data, and the Millingimby has the largest. So we choose to have this one as the high ranking, but it could be for another reason if you have tensor data that you're more certain of, or a newer sensor, a newer survey, you can specify that as your high ranking.
Right. I couldn't see Can you specify the order of every single one?
No, you can't specify a listing order of every single one by the number, but you can by taking a look at your data and specifying what one's the highest in that region and not. There's a case obviously where you begin having 4 overlap grids and you can't tell the system what grid is numbers 2 and 3, but you definitely can force 1 and 4 in your order, where 1 being the highest priority and 4 being your lowest. And that's something that could take some development here with grid merge, being able to force an order. The menu itself doesn't actually allow you to do this so currently.
I thought with our Australia mergers, we specified the order of every single one. Was I wrong?
I'm not sure how the operation can work back end. I know there's a lot of, this tool has a very long history with some very serious applications. There are some back end things that I don't know how they operate. There are some finer settings for using line data and surveying back and complex things. So there may be perhaps a way in the old job syntax to specify a forced order, because there is a way, the system does create an order using that default criteria. So there perhaps is a way to override it. I can definitely look up with Des how that was done in the past.
Yeah, I'd certainly be interested
Forced order
in knowing that going into the future.
Yeah.
That'd be my natural inclination, would be to want to do that.
Yeah, sure. Let me just make a note there. High, low.
Yeah, because usually you just specify the one high ranking, and if you wanted all of the other ones to be low, you just grab all of them and put it in, and there's no specific order as far as I know when I've been doing that. Matthew, I don't know if you can also comment on that.
I have a feeling it's alphabetical order. In other words, based on.
It is alphabetical in the GUI, but that's a bit of a lie in terms of what the order actually is. Once you specify multiple highs or multiple lows, it will use that default criteria of cell size and number of points within the sample, number of sample points within the data. So if you have a really large dimension grid with fine cell size, it's going to rank higher than a small grid of the same cell size. But there may be a way to override it, and I'll definitely ask Des how that works.
It's this grid that's kind of staggered in the middle there. Yeah. That has overlaps on the northern and the southeastern edge.
This region here that I'm circling.
Yeah. Like you'd have to get that right according to your desires. You'd have to be able to specify the order of everything to get that right.
In this situation here, if we wanted this grid here in the middle of the two to be higher than these area 1, and I believe this is TCC West, you just specify this as the high ranking. So this would be a high ranking and this would be a high ranking, and so they would be on top. But again, that's a use case that's limited to just 3 layers, not 4.
So that means so that means you put the 2 grades at the high ranking.
Yes, you can specify as many high ranking grids as you want, but in terms of what rank within that high ranking order, at the moment you can't specify.
Yeah.
Okay. Yeah, no, there must be a way. Yeah, thanks for checking up on that. Yeah.
I'm just going to close these and set it out of the way, and we'll head back into. Sorry.
When you do the DC shift, what is when it's shifting them? Is it just using the overlap between? It's the base grid that it's DC shifting to.
Yes, so everything will get shifted so that the overlap regions line up to the base grid. So a grid with an average value of 5,000 nanoteslas is going to be brought up to the 49,000 nanoteslas in this example. And it's only to it's only a very rough, well, I won't say rough. It's a fit on the overlaps, so the overlaps line up, but obviously there's going to be differences between the two grids at this point still, and that's where the surface adjust comes in to minimize those.
So the DC shift is going to work out between any pair of grids what the overlap pixels are, and then work out the least squares DC shift to the whole lot.
Yeah, and it'll apply it to the whole grid and bring that all up to value, and apply a correction, a single correction to it.
So I've only ever used a base grid for that. So are you saying you don't necessarily have to specify a base grid at that step?
No, you do. You do definitely have to specify a base grid so that the system knows where you want the data to lie, whether you want it to be down, centered around 0, or still containing the Earth's magnetic field, or whatever it might be. You definitely need to specify a base grid, but it will bring all that data up with a single correction, or many single corrections to each grid so that they're all at one surface, or approximately. Does that clear it up? Sorry.
Yep.
Yeah. Cool.
Yeah. No, I can see how that works out. Yeah. But I just wanted to know whether it was just the overlap between each pair of grids that have an overlap.
Yeah. So the next step here in the grid merge process is the surface adjust. So
I see what you're saying, Rich. Sorry for stopping. I see what you're saying, Richard. So yeah, I always used to do the DC shift without cutting holes in the base grid, so that you get a maximum overlap. Because I always was worried about that, the feature as well.
Yes. Yeah.
All right. I think that might be lost on me. But yeah, that's all right.
So a long running discussion elsewhere. Yeah.
Okay, excellent. Right. Sorry, I got lost. The next step is the surface adjust. So this is that smaller correction between the overlaps. So we start seeing the differences being minimized iteratively. So the input to this process is the output from the previous step, which is the DC shift. So I'll head into level grids in the grid merge tool, and I'll go and do my surface adjust again. I'll choose the demo DC as my input directory, and I'll specify any file. I won't use any other directory, and I'll specify my next output as just demo surface adjust SA. It has remembered my ranking from earlier. So in a single grid merge window, it's going to remember what data you specified in your previous ranks. And just to demonstrate, you can select multiple high ranking grids, and it's going to put them in an alphabetical order in the GUI at least. But that's just a software program sorting, lost. So press OK, I keep the ranks just the same, as I need to change them, and I can now specify my surface adjust parameters. So this uses polynomial, it fits polynomials to the surfaces of each grid and across all grids. But for this case, we want to use a polynomial of first degree. So I leave all the other settings as is, and I just press OK, and I proceed with my surface adjust. Incredibly quick with this data set. The feather merge by far is the slowest process in the grid merge tool. The DC and the surface adjust are rather quick.
Excuse me, Tim.
Sorry, Riordan.
Sorry.
I haven't changed my name actually.
Well, yeah, Riordan. Yeah, sorry. Can you go through each of those, those parameters that you just showed, the surface adjust parameters, and expand a little bit on it, please?
Yeah, no worries. Yeah. Sorry, let's get through that. And here we are. We have the surface adjust, the allow DC shifts if the degree is greater than a specified value, which is greater than the surface degree specified here. So it can go back in DC shift. We can specify the minimum overlap limit and the maximum overlap limit. So it's not going to consider the entire overlap region if there's more than 5,000, or it's going to consider overlap region up until 5,000 cells. And an overlap region needs to have at least 500 cells. And that's just a point for statistical significance. Too few and the polynomial may not even fit correctly. We specify a number of iterations that we want to go through. So the surface adjust will continue up until the maximum iterations that you specify, or it will halt at a moment that it falls below the residual set in the next text box. So you can set a maximum residual, so the acceptable limit that you want to achieve, and it will, yep.
Yeah, just so how do you choose that maximum residual value? Is it based on how your grid is and all that, or is there a rule of thumb for that?
Is there an error of
a rule of thumb to choose that value? To specify the value.
It can be specified based on what your data is and what you think an acceptable limit is between two surfaces. If you're finding that two data sets are vastly different or one's far noisier, you're going to need to maybe modify or make the residual a little bit larger.
And
yeah,
that value is, yeah, okay.
So it's the residual, I believe it's referring to the changes made to each cell between one process to the next step. So it's value at step 1 versus value at step 2, and it takes it looks at the change. So if the change is below a certain value, and I believe it's not an absolute value, I believe it's relative, it'll consider it successful.
So this is fitting a trend surface to the difference between pairs of grids.
Yes, yeah.
Yep, okay.
And it'll go back and correct that each time until it either hits the maximum iterations and your
iteration, okay.
Yeah, otherwise it'll, if it takes 10 passes to get through, it's going to stop there and never get to the 100. It's going to say it's acceptable. So you can set this as fine as you want, but that's up to your discretion. The surface degree is the polynomial degree that you wish to fit. Noisier data, fit a 2 or a 3, but do not go above a 3. Doesn't really make sense.
So what's the maximum? What's the range?
Sorry, the range is 1 to 3 for your polynomial degrees. I believe it will accept a value of 4, but we don't recommend it because it doesn't really make a whole lot of sense to us here at Intrepid.
So the bigger the value, the noisier the. Sorry, Richard.
Yes, sorry. The bigger the value, the noisier the data.
The data.
You're trying to fit. So there was a case a while ago. I was looking at some grid merge data, and there was a very strong peak in the overlap area, where very close points. One was 10,000, one was 14,000 nanoteslas, and it was causing an entire issue throughout the entire grid where an artifact is appearing. So by bumping up the surface adjust degree, it allowed for a bit better of a fit along that area to minimize that difference between the two cells. Because obviously, first degree polynomial isn't going to fit, sharp peaks to items, especially over a long area. It's going to fit nice little trends.
Default is a second order fit. Is that correct?
Yeah, the default is a second order fit. If you have nice data, you can go down to 1. But the default is 2.
Is there any reason why you wouldn't want to set the max overlap limit to be a very large number? Is there any reason why you wouldn't want to use the whole overlap?
There are cases where you don't want to consider data on the internal of the grid for what you're fixing. It is dependent on your data. I couldn't think of any cases where you'll suffer by putting it up higher, except that you have to consider more data and the process will become more heavy.
Yeah, I'm just wondering, how does it choose? Say you set 5,000 and it's easy in a grid to have, 100,000 cells in an overlap.
Yeah.
How does it choose the 5,000?
It's the 5,000 over the border of your high ranking grid. So it's going to pick a region around that that's significant enough to correct itself.
Yeah. Personally, I'd be sticking something, like 1 trillion in there.
Right, yeah.
Just to make sure everything.
Make sure you got every one of them.
Yeah, right, yeah.
Yeah. So is that, so that's so the maximum is 5,000? Are we limited to 5,000, or can we put a bigger value?
Oh, you can put it.
Does the software allow you to put a larger value?
Yes,
is that,
it will allow
okay.
you to put larger.
Okay.
Got to a point. I think the program will stop at a certain number of bits, but you can put a larger value there for certain. Certainly. There's a difference limit. So, head up. We have degree 1 limit and degree n limit. These two are a bit lost on me. I don't touch them. There is documentation covering it. I believe it covers the percentage of overlap compared to the rest of the grid. So if you have a grid where 60% is overlapping another grid, you have, if the 20% of the overlap, I choose my words here carefully.
I don't think I've ever changed those parameters, but I'm not sure why not.
So if the overlap is far too small compared to the rest of the size, into like the ratio of the rest of the grid, it may fall outside these limits set here. So if the overlap represents an area of 2 or 3% of the total grid, it may not be sufficient. So you can specify here, control what borders get merged and what don't. And the final setting is the difference limit. So if a difference of greater than 99 is detected when it's fitting the surface adjustment, it's going to assume that it's just noisy data. I don't want to fit a trend to it, and it's going to ignore that point. And this is just to stop the polynomials just walking off and grabbing really absurd values that don't make a whole lot of sense for a trend. And that just kind of protects it from itself. So that will depend on your own feel about the data. If it's particularly noisy, if there are big jumps, big spikes throughout that haven't been removed, you might want to bump the difference limit up. Or alternatively, if you think the data is really nice and smooth, you can bring it down by a good portion. But the 99 is a default limit that we use here, and we don't change it very often. So I'm going to press OK again, and because I've already done the process, I'm just going to skip it for now.
This is probably a dumb question, but these grids have got different cell sizes and origins?
Correct, yeah. So I'll head into the data itself, the raw, so we can have a look. So we have area 1, area 2, Beatrice, and the 2 large Melangimbi and the West Arnhem. So these have a cell size of 100, with different origins and the centroid origin, compared to Beatrice here, which has a 50 cell size and a different origin again.
So what's controlling the resampling? You'd have to resample.
You do resample, yeah.
So which one is it? The highest ranking one?
It's the base grid.
It's the base grid.
So sorry, no, that's wrong. The high ranking is the one that gets resampled to. So the rest of the grids will resample.
That's the cell size.
Cell size of the highest ranking grid.
That's the cell size, but when it comes to the shifting, it takes the top left corner of the most northwest grid as the origin, and then shifts the rest of them around that.
Geez, that's a tricky combination to think of.
Yeah. Centroids and shifting some I don't like thinking about, so I agree.
Does it do that job? Does it do that job of resampling anywhere? Like, I haven't seen it in this list. It would seem to be efficient to me to do that resampling and store some resampled grids somewhere. Doesn't do that?
There will be a temp directory step of feather merging where the resample happens. Yeah. But for now, the grids are still their original their original sizes, 60 and 50.
So in the feather merge, put a lot of files into your folder.
It does. It dumps a number of temp files out, and if I am correct, there's also another set of them that are stored in the official Intrepid temp area, which I believe is your documents or your app data area.
That's what I was filling up your C drive event.
So yeah, it's certainly something, because if you're using large grids, you're using large grids, perhaps set a rule on your windows to clear out a bit more often than not, but also not too often that you're deleting data that your computer still might be using if you're doing a really long job. But Intrepid does a job of managing that for you for the most part. So if you leave it to the areas that it wants to go, it'll do the job. The final step is the feather merge, which is probably the crucial part. So we'll head back into our grid merge tool, and we'll choose to do our final step, which is merge grids, and we'll merge and feather the grids. Now we'll specify the input directory as the surface adjust, as the previous ones, and we won't use any other directories. And we finally get to specify our final image. So we'll call this one as demo. And .ers. By default, it's going to pick the ERS anyway, but good practice to force it. Because I've closed the... sorry about this, guys. It's grabbed 2 directories by accident. So I'm just going to close this and fix that. So we're going to head back in from a new window entirely. And
just while you're doing that,
yep.
Dumb question. Are you using grids that are in projected coordinates or longs and lats and longs?
Lats, sorry. Projected.
They're projected.
Yeah.
Okay.
Sorry, took me a second to think there. Yeah, they are projected. It does support geodetic, but I believe they get converted anyway during the process. I would have to test and get back to you if that was the case. Yeah. What was I up to? Grid match. Sorry, get rid of that. We'll merge grids and we'll merge and feather the grids. Sorry about this. I already had the window open. Des is joining. It's all right.
Momentarily.
Yep, just doing the last step in the feather merge, and then we're heading off into the gridding operations. So we input our surface adjust directory, and we'll choose not to use another directory. We'll finally get to specify our output image again. Now we get to re-specify our base grids because I did close the window, it has forgotten. So I'll use the West Arnhem sub as my base. Beatrice is my high ranking. And the Millingimby sub as the low rank grid. At this point here, we have some extra settings for the feathering process. We have the option to trim the resampled grid. So it's going to step in a few cells from the grid's extents before merging to remove any extra extrapolated cells. So if your gridding process has
one cell.
One cell, yeah. If your gridding process has extrapolated one cell over, you can trim that back in this step here. Once again, we specify our overlap limit that we wish to the lower threshold, so it has to have more than 500 to be significant. We can specify a filter length that we're going to smooth over. The larger the length here, the smoother the grid. It's going to use a larger region to smooth over. We can specify the number of iterations. So you can use 3, you can use 6, any integer you wish. And what's going to happen is that it's going to smooth at 5,000, and then it's going to smooth at 2,500, and then finally at 1,250 in a 3-step process. So it's going to fit smoothing over 5,000, then trim the boundary, the overlap, trim filter again at 2,500, trim again, and then filter at 1,250.
I'm having trouble visualizing what the filter length means in terms of overlap regions, bits of grid that don't overlap.
It's going to apply a correction into the grids, possibly outside of where they overlap. And it's going to step through and remove wavelengths at a step down in halves each time from your specified filter length.
So does it take each grid and come in 5,000 meters from every side?
I believe it puts 5,000 over. I would have to I have a difference grid on my computer in the other the office. I was looking at the filter length. I don't believe it's 5,000 each way. I think it's 2,500 each way. It plays a 5,000 length over the top of the boundary. So 2,500 in each direction.
So is it just, is it filtering with that filter length over the entire grid, or just that, in this case, 2,500 out from every edge?
From every edge. So it will extend slightly into your grid, but it's not going to cover the whole grid. It's just over the edge itself. It's just.
And when it says,
sorry.
And when it says filter, what does that actually mean? Does it mean? Well, I've got no idea what it means. What does it mean?
Don't know the mathematics behind what filter it is applied. The coverage that I get is that it's a smoothing process to make sure that the edge is seamless, so you get a cohesive portion over the edge, so you're not getting any jagged parts or edge artifacts. I don't know what type of filter it is. I'll have to check that up.
Yeah, if you could chase up what that actually means, that would help me in my mind.
Yeah.
Yvette knows that I'm probably itching to get a pen and scribble something on a piece of paper at this point.
I'm sure you've already scribbled something, Richard.
Yeah. I'm trying to draw something. It's not working. Yeah, just not quite. I need to sort of know what it was trying to do to understand what to put there.
Sure, yeah.
Because if I had a different project, I don't know, 500 might be the magic number, or 600 or 10,000, or how do I know?
Yeah, of course. So let me just have a look. I'm just seeing if there's a discussion in the documentation.
Yep.
To answer that question now.
Yep.
It's small.
I actually thought the smoothing iterations were different to the number of jumps. I've obviously got that wrong. I thought smoothing iteration was a further process after you'd done the feather merge. It was then going to run 3 smoothing iterations. So obviously I've misunderstood that.
I actually believe you might be correct there. I think you are. There's a number of passes setting within the Intrepid, but it doesn't show up in the GUI. And there's the smoothing iterations, and they are different. So the number of passes, the number of jumps is 6 by default, and that doesn't show up in the GUI to be changed. But the smoothing iterations do, and that's the default to 3. So I am mistaken. I spoke incorrectly there. So you're correct. They are different. The number of passes to the number of jumps is by default 6, and that doesn't appear here in this GUI. Excellent. I'll make a point of that.
Yeah, we better know what the smoothing means as well.
Yeah.
Could mean a lot of evils.
Passes. And what is smoothing? Right, I can pass those questions on to Des and get sufficient answers to you guys.
Could you also just double check about the projection on the fly that we talked about before? So if you're using long and lat grids, if it's doing if it really is doing a projection on the fly.
Let's get stage in.
Yeah, because otherwise these filter lengths are going to be radically different if it's not.
Yes, of course. Yeah.
And you'd have to know what sort of projection to know the right number.
Yeah, exactly. Yeah. Finally, we're going to leave these settings as default and just run through the process anyway. So I'm going to press OK. And the final question is if we want to do any clipping. So if we have a predefined polygon or a survey area that's over a boundary that we want to look at in particular, we can, we can do that here. But in this case, we're going to look at all the grids together. So we'll choose no clipping. And we'll proceed with the feather and merge. which is a slightly slower process than the other ones. And as mentioned before, it does create these temporary files that sit around for a bit. It's going to take a bit of a longer on this computer, I believe. It's a bit slower than mine. There we are, completed. So we finally get an output. We'll get a final output for the, here's the answer. The interpolation method is Newton's fourth order. A feathering filter pass has these lengths here with 6 jumps. And we have our origins and cell size on the final output grid that's used here. Cool. So now that we have outputted our final grid, we can take a look in 3D Explore, and then we'll head over to gridding operations. So it's created temporary files in both directories as it's created the merge, both in the working SA and the final output area. So demo merge, we'll open the 3D Explorer just quickly. So by selecting the file and heading straight to the Visual 3D Explorer, it's going to open the file straight away into the 3D viewer, which is a nice little feature. So here we have the final merge grid. And what we can do as a bit of a quality assurance check is we can take this to a sine angle drape and drop the inclination right down. And depending on the data and how well the merge was done, we will see some edge artifacts along the boundaries, or we won't see any. So I know there's one long vertical one or boundary through this region here, but there is no clear artifact along this line here. So in this case, we can assume that it's been a well-completed merge. But by doing this sine angle drape, it does accentuate the issues. And what you can do further in grid filtering, which was described today by Tim, is you can take the first vertical derivative instead. And that's going to really show off any edges or any issues with the grid merge process if you want to go back and change the filter length or some settings and smoothing. But yeah, so that's the final output of a grid merge product. And in terms of what the initial image I showed at the very start explaining variable density, that's through this region here. There's a little bit of a snippet, and then this entire thing. So you can do 2 grids, you can do as many grids as you want for your grid merge. Excellent. Is there any questions now just for the grid merge besides the ones that have been asked, or should I move straight into just the gridding operations tool and just demonstrate it?
I'm good with the current list.
Cool.
Yeah, I've just got one sort of observation that I'm personally having a bit of trouble with the merge and feather step.
Yeah.
But that's okay. I think that can maybe get to the bottom of it with some of those other questions that we've asked already.
Sure, yeah. And as always, Intrepid do have a support email, which is hooked up to, we can take in data and have a look. I do the testing initially, and then I can pass on any issues that we notice with the process to Des, because as always, we want to be able to match people's data and address problems that people are having with geophysics. So if you have any issues that you don't feel as though you want to address straight away or put the work in, we can definitely take a look and make sure that we can address them for you before you go and dedicate that time in, as always. So next is the gridding operations. So this is just a quick Java tool that was put together, I believe, about 2 years ago. And it was just a rewrite of the old tool. So it contains a series of root arithmetic, perhaps you can call it, a series of functions that are just put into this list here that operate on grids and grids only. It's going to support ERS files by default and it expects those, but there are other grid files that Intrepid support that will work in this tool. So we can specify at the top of the window, we have the ability to open our task files and run the program, but alternatively, we always have the run at the bottom. We can save task files out, so any process that we do here, once we set the parameters in the GUI, we can save them as a task file and run them again in the future, or modify them as we see fit in the text editor. There's some options to use different types of pathing. This is purely just in the GUI. If you wish to specify using absolute or as relative, but the system is smart enough to pick up on those and it will automatically know what your working directory is. And finally, we do have the help and the new online help, which will open the Intrepid documents to our website, which will have all the coverage of the current functions. So to start off, we have some tensor operations. So from here, we can create a tensor grid from its parts. So if we have Falcon data or we have just tensor data, we can specify these values, put it in a maximum trace area that's accessible, and we specify an output grid to the working directory that we're in. And this is a pretty standard. This GUI will modify itself as you choose the functions to provide you with the settings that you need to do these steps. We have some extract components, which will take your input grid and extract a specified tensor component from it. So if I were to head into the tensor cookbook area, I can give a demonstration of this. So I head up into examples, into cookbooks, tensors, and I'll use the full tensor, Arizona, Montezuma grids, and I'll take a rotated grid here, the Bugay area. So that's the input, and I can take any query from this and export it to a single scalar grid as you see fit and as you need, and then specify an output file and run that. So what we can do now is actually just a quick demonstration of this. So I want to look at the, we'll say the horizontal gradient. Output the file, and I can just specify demo and press enter. Sorry, I'll press the look for button, and it's going to write to this location here, which isn't ideal, but at least I know where it is. So I'll run that program. And now we have taken a demo grid, which is a scalar grid of a tensor component from the input grid. So a similar process will happen for any other function. So I'll just quickly go through rather than demonstrate them all and explain. All of them have a tooltip. So we have resampling methods that use Newton fourth order. We have cubic spline, cubic polynomial, and minimum curvature resampling. We have the option to resample and resize. So this allows you to shift your grid and your cell sizes if you wish.
I've got a question at this point. So when you choose the resize and resample, do you get, I mean, if you use a task file, can you choose the type of resampling, or is that set at, say, Newtonian fourth order?
This one here is set at the cubic polynomial method.
Cubic polynomial, okay.
Yeah, and it won't conduct any smoothing either.
Okay, and can you adjust that in a task file?
I do not believe so. What we can do though is we can actually set up a system to do that. So let me just input a scalar grid just for safety's sake, because I don't know tensors in terms of resampling. So head and guided tours, and we'll just grab an LB data set quickly. We got cell size at 25, and we'll save the task file out. We'll grid op task, and that's probably just enough. I'll enter that. So now it's saved the task file. It hasn't actually run the process, and what I can do is go into Intrepid and find that task file and open with our registered app. So from here, the resample is the message that we look for, and by it's saved out the X-min and Y-min values as well as the cell size. But from this, we can tell that resample is what we're looking for, and the method is to resample. But this is a part of grid op. So method of understanding this is to head into the protobuf documentation. We'll head into the Intrepid task area, and we're just going to look for a quick search for resample. So we have some for the resampler tool itself. We have a different tool here, and what we'll actually better to look for is the grid op and its messages. So we have grid operations integer here, and we have a number of messages here specified. So resample here is an optional method within the file, but it doesn't have any extra things, I believe. Yep. So to confirm that, this is the settings that are available for that method, none of which are a method to change what interpolation method it uses. Yeah, so can't do it there, but in future, if it was required for us to have a resampling method or a resize method that used Newton fourth order, that could be requested of us, and we could put some development time into making that.
Polynomials. Cubic polynomials.
Yep, sorry. Yeah, okay. So let's get rid of this ProBuff documentation. And we'll head back into the gridding menu for the last little bit. So the number of tools throughout here, we have subsampling as well. So we'll decrease the resolution of the grid. So we're decimating in that sense. And you can specify where the first sample is and the number of samples as well. And most of the text boxes within this Java GUI will have tooltips to help direct you along through the process. We have rotation as well, which was a topic of discussion yesterday. So in this set here, it's going to take the grid, your input grid. It will either rotate it through an angle, so specify to rotate by a certain number of degrees, or it will take an output angle. So if you want it to sit at 157 or whatever, it'll use that. So you can toggle that here using the output rotation angle or the rotate through angle. And it uses an interpolation method when it rotates so that the data stays in the same geospatial location, but it may now exist in a slightly different cell. And yeah, you can choose which rotation method you want to use there. We have the option to dump the data set out into rows or columns, which is a really simple process. You can choose the coordinate system. That's basically the only setting there. We have the get band and the append band system. So we can have multi-banded grid data. If you want to extract one band from it, you can use this if you have a multi-band grid, i.e. radiometrics. And you can pull that out into its own. Alternatively, if you want to create a radiometrics grid from 3 separate grids, you use this process 3 times over. So the input becomes a reference for each step, and you go through and create your multi-band grid. We have options to change the precision of your data, and that only works on scalar data. Homogenize the grids, so this will take a series of grids that are similar spatially. Has to be very close to identical, but not perfect. And I'll make it so that cell size and the bounds all match, which is a bit better for other grid processes. A nice quality assurance, a quality control method is to take differences between your grids, and that can be done here in the grid opting tool. So we'll take an input grid and a reference grid. It'll subtract the input grid from the reference grid before saving it out. The bounds and cell size, again, need to be similar but not identical for this to work. Yeah, so we have an input grid and a reference grid, and you just press run, and it's going to output a difference grid for you. You can detrend from the grid with a defined polynomial or degree of polynomial. And the last few settings, you can generate a geomagnetic or an IGRF model for a input grid. So if I have a data set that I don't have the IGRF for and I want to see what it is over that region, input that is my input grid, and it's going to calculate the IGRF model. So you're going to get the inclination, declination, and the amplitude. So 3 output grids for that.
Which IGRF model?
I believe it's the latest. For any date you choose, it'll take the file coordinates as the input. I'm not super familiar with the happenings and goings of what models are currently in place. My understanding, this is the latest one, the up-to-date one.
Okay, but it would be good to have that included in the tool to say using this IGRF model.
IGRF model declaration. Cool. All right, I'll put that down as well to discuss. Yeah, so this can take your own altitude and latitude that you wish. So you can force it to do what you want. Otherwise, the last step is the outline, which we talked about earlier. So this is going to outline a shapefile or a .dir, as well as a .ds is possible as well. However, .dir and .shape work just fine. So I'll quickly grab a rotated grid with a bit of a funny shape to demonstrate the outline tool. We'll head back into tensors and we'll just grab that rotated grid from earlier. So this is slightly different to the grid merge outline. So this will create a line instead of a grid. So I'll just output a file called grid outline. And I'll save it and run that task file. Cool. That's up here in cookbooks. Yes. and that's produced a, by default, .shape file to take a look at. So a quick outline. So this isn't as quick to do as a grid merge tool, which will take a whole directory and calculate the outlines. You would have to do this process each time for each grid, but that's something that you can do there. And then you can create finally a null grid. So if you have some processes that you need a null grid that's identical in cells and dimensions to your input, this is the tool to do that. Other than that, that's the gridding operation tool. It's just a small wizard. And it actually does run off the protobuf syntax if you're interested in how we use it internally. This system here uses that. It'll write from those protos to create task files and then run those in the back end. So this is a task file wizard, essentially.
Is there an operation to fill holes in a grid?
Not in the gridding operation tool. Besides the internal holes from the actual gridding process itself, no. If you want to pad out grids, that's something that could be discussed, but it's not something that we support currently. Are you talking about corner, like the holes on the edge of the grid, or the internal ones?
Well, I mean, both would be good, but I was actually asking about internal ones. But yeah, padding out.
Certainly, the internal ones can be done using the gridding tool at the very first step. I don't believe there's a gridding operation to interpolate over a hole. However, the resampling methods do interpolate, so I imagine we might be able to put something in there to step over any holes that it finds. Yeah, that's a question I'll ask. If there's something in the back end to interpolate over holes once you already have a grid.
And also add padding would be great as well.
Yeah, interpolate over holes and stop working. Of course it did.
This what's come up on the screen at the moment is one that's intrigued me. A Newton fourth order. Is there a reference to the maths of what that actually means? It's just something I'm not familiar with. And
so the Newton fourth order is a really good difference, a really good filter to detect noise in data. I'm not sure how it's used for interpolation, but for smoothing, I do know it's a noise reduction method. The math itself might be covered in a documentation. Otherwise, there might be a paper floating around with the original method for this.
Yeah, if you could take a look for that.
Yeah.
That'd be great. Really appreciate that. Yeah.
Ready. Is there any other questions today? So I think that'll be all. There was no questions. Sorry.
Yeah.
No one's in chat. Creates a great graphic. Okay, excellent. Thank you all for listening today. I believe there's still training tomorrow. I have to check the agenda, but I have another one next week, I believe, if people are attending for quality assurance and quality control using Intrepid tools. And I'll be running that with Tim. Other than that, I hope you all have a nice day. Thank you very much for attending.
Thank you.
Thank you. Thank you for doing so.
Thanks very much.
Cheers.
Thank you. Bye.
Bye.
Bye, everyone.
Cheers,
Bye.
everyone.